Hello, and welcome to James. We are Andrew, Esam, Indika, Robert, and Samuel, a team of 5 computer science majors at McMaster University. And in this video, we will be demonstrating the product of our work over the past academic year. The result of our effort is James, a web application for research in the digital humanities. We will tell you all about what problem our application addresses and how we work together to build a solution to this problem and contribute a valuable tool for digital humanities research. So, where did it all begin? I mentioned that James is a tool for the digital humanities. What is that? The digital humanities is an academic discipline that uses software tools to assist humanities research, and the rapid expansion of the power of modern software has led to a similar explosion in the popularity and capabilities of the discipline. Techniques used to analyze text are referred to as natural language processing. Now, huge volumes of text can be processed digitally in minutes instead of months, and machine learning has allowed analyses never before possible. Of course then, the capabilities of the digital humanities depend directly on the available tools. One very popular natural language processing technique is topic modeling, a category of statistical algorithms that cluster words in a text together to create a model of the topics present in the text. This is clearly a powerful tool for analyzing large bodies of work. However, Dr. Alexander Klein, a digital humanities researcher and director of the Bertrand Russell Research Center here at McMaster, came to us with a major limitation on topic modeling. In order to really understand a work, knowing the mere presence of a topic is not enough. Obviously, we also need to know the author's opinion towards it. Are they arguing for an idea or against it? This is a pretty big gap, and there doesn't exist a tool in the market yet that attempts to deal with this gap. So, how do we solve this problem? With sentiment analysis. Sentiment analysis is another popular natural language processing technique used to determine whether a piece of text is showing positive, negative, or neutral sentiment. One well-known use case of sentiment analysis is analyzing product sentiment in customer feedback data, so businesses can better understand the needs and opinions of their customers. If we could combine topic modeling with sentiment analysis, we could create a tool for digital humanities research that would be able to analyze a text for not only the topics present, but also the author's attitude towards these topics. And that's exactly what we did. Dr. Klein was looking for a tool that could perform this kind of analysis on the works of philosopher and psychologist William James, and so James was born.
James consists of 2 parts: topic modeling and sentiment analysis. James has a few basic topic modeling components. The elements of a topic model are a cluster of words associated together through unsupervised machine learning. James requires you to load your corpus text and specify your desired number of topics. Each topic is represented by word weight pairs, where the weight indicates the strength of a word's association to that topic. In the results for each input document, James will display in what proportion each topic belongs to each document, and the sentiment score for each topic. The results also provide a coherence score, which is a measure for assessing the quality of learned topics, and 5 example sentences that best associate with each topic.
The second part of James is the sentiment analysis. We used supervised machine learning to train 2 sentiment classification models. One that can predict whether a sentence is demonstrating a positive or negative sentiment, and another which can predict whether a sentence is demonstrating support or opposition. The models take a sentence as an input, and then outputs a score between 0 and 1, where, depending on which model the user has chosen, a score of 0 is a negative or opposition sentiment, and a score of 1 is a positive or a support sentiment. With James, we make sentiment predictions on every sentence related to a given topic, in order to calculate the entire sentiment score for that topic.
Usage of our application begins by navigating to our site, the UI for which can be seen here. So further down on the page, we have some instructions on how to use James, as well as how to interpret the results, as well as a little section about us. But the core functionality of our application lies here at the top. And this process begins by uploading a file that contains text that we wish to analyze. So if I select this file here, we can see that it has now been uploaded. File 1, example text, the name of the file, and the size. But the calculate button is still grayed out here. So in order to complete the process, we need to select a number of topics that we suspect will be contained within this text. So here I've selected 2, but this can be an integer between 1 and 200. So the next section is the sentiment data set. Sentiment analysis is a supervised learning process. So effectively, we've included two separate data sets for the model to be trained on. So we have support and object, or positive and negative. And so the user has the ability to select one of these two as they see fit for their specific data being uploaded. So now that we've gone ahead and selected positive and negative data, we can actually go ahead and click calculate, and this will make a request to the backend. So now that the response has been returned, we can see that the results are here on the screen. And so these are broken down into two separate sections. So the first one is topics from the topic modeling. And so here, each word in the topic has a weight that corresponds to how significant that word was to this topic. And so the higher the number, the more it was found to be significant in this topic. Each word also has a stem. And so this stem is a result of the topic modeling stemming process. And this is used to essentially find words that are found to be similar and then associate them together. So down here at the bottom, we also have some example sentences along with a topic weight for those as well. So for this particular run, we can see here that religious was found to be the #1 most significant word with this weighting, followed by faith and question. And so based on the content that we input, this sort of makes sense. And then one other cool feature that we have with this as well is the ability to hide topics. So that occurs here in the topic section, but also down here in the sentiment analysis section. So essentially what we have here is a topic number that corresponds to the topics above, as well as a weight, and then a sentiment score. So for this particular run, we can see that both topic 1 and 2 were discussed about the same amount, and neither of them were discussed in a very positive light, as 0 corresponds to a negative sentiment and 1 corresponds to a positive sentiment. So if I scroll back up here to the top, now that we have our results and we've analyzed them a little bit, we can actually go ahead and download our results. So if I open this up, we can see that we have the results for topic modeling, topic #1, as well as topic #2, and then down here at the bottom we have the sentiment. But if we go back to the UI and we actually hide one of these topics from the UI, it also hides it from the results. So this is just a handy little feature for ignoring some sections of the data that might not necessarily be as useful.
The James group faced 3 main design challenges for topic modeling. The first challenge was whether to write a machine learning algorithm from scratch. This was not feasible given our inexperience on the subject, and we ultimately chose a backend library called latent Dirichlet allocation. The second challenge was to determine which topics belong to which texts. Since each sentence is weighted by topic, we can sum weights for each sentence belonging to a text. James can quickly deduce what topics each text is talking about. The third challenge was to allocate sentiment to the text. Since each sentence is weighted by topic, we can run the sentiment model on each sentence and sum the sentiment scores. The result is a list of sentiment scores by topic for each document.
There were also a few notable design challenges we faced when implementing the sentiment analysis portion of our project. The 3 biggest challenges we faced were finding good training data, adding a new sentiment model, and deciding to move towards using neural networks. Sentiment analysis is often done using supervised machine learning techniques. This means labeled training data is needed to train an algorithm to make the predictions. One challenge with creating the algorithms for James was finding a dataset of labeled training data for sentiment analysis. This dataset had to contain both text data and its corresponding sentiment label. We started out with labeled Twitter data, but given our application would focus on analyzing philosophy texts, we decided the considerable contrast between how philosophy corpora were written 200 years ago and how tweets are written today was going to affect our predictions. One option was to create a dataset containing text data from philosophers in William James's era, but due to time constraints and limited resources, we decided against the solution. Ultimately, we went with a dataset consisting of reviews from Yelp, Amazon, and IMDb. The rationale behind this decision was that if we cannot find the ideal dataset to train our model, we could instead aim towards a larger and more diverse dataset that can allow our model to generalize well. Additionally, we found that these reviews were better written than the original Twitter dataset, and thus proved to be better suited for the application. Another major design decision occurred when we came across a dataset containing congressional floor debates. This dataset would contain texts, which more closely resembles philosophy text. The labels, however, were support and oppose instead of positive and negative. After discussion with Dr. Klein, we decided that we would create a second sentiment model. This model would be able to analyze the support-oppose sentiment of a given topic. The user would then be able to switch and choose which model they would like to use for their analysis. This change provided greater versatility to our product by opening new doors to how the text analysis can be completed. The final major design decision for the sentiment analysis was switching from a naive Bayes classifier to using a recurrent neural network. Our original implementation of sentiment analysis utilized a naive Bayes classifier, a bag of words model which works by looking at the probabilities of a given word being in a piece of text with a given label. It does this naively, so each word in a text is considered independently of other words. A recurrent neural network, however, processes sequences one element at a time while retaining memory of what has previously occurred in the sequence. This ability to consider the entire context of a sequence of data makes it capable of providing a more accurate sentiment analysis compared to the naive Bayes approach. This design decision proved to have a steep learning curve, as many of us were new to using neural networks. It required an understanding of the theory behind neural networks, the long short-term memory RNN architecture, and implementations using TensorFlow and Keras. The outcome, however, was a more robust sentiment analysis model, which provided increased accuracy in its classifications when compared to the naive Bayes.
When designing our user interface, the first challenge was to decide how we want users to access our application. We considered making downloadable software or a command line tool, but we ultimately decided that a web application would be the best choice. A web app makes our product platform independent and allows any user with a web browser to access our product. Following that, another big challenge for us was to make the application user-friendly. As our users can be from a wide range of technical backgrounds, building a UI that follows user-friendly design principles was very important. For example, the page follows a simple, consistent format, provides comprehensive user feedback, and makes the user feel in control. Another design challenge we faced was how were we going to return the results to the user. As seen in the demo, the result is output to the UI in an easy-to-read and interactive format, allowing the user to hide certain topics or see example sentences from the text. To allow the user to be able to quickly use that information in other formats, such as input for a graph or another program, users can download the results as a CSV immediately after receipt. And that brings us to the conclusion of our presentation. While we believe our solution of combining topic modeling and sentiment analysis to be a breakthrough for researchers in the digital humanities, we hope you find James to not only be a compelling and useful tool in natural language processing, but also something to build on for years to come. From the team that built James, thank you.